put out a paper in 2014. In 2015, Dr. Talk put out another paper and he quoted this to see exactly the way it worked. Because before they didn't understand how it worked. And now I'm about to show us exactly how his system works, that basically I capitalize on to show you exactly how it works. Now, with iron, remember it's using an iron aerial system. Now, the aerial, the carbon is a carbon is a carbon. The electron density of carbon is electron density of carbon. The carbon is a carbon is a carbon. So, with my system, I'm not going to use a big bulky system. I'm going to use a small system. Because the chemistry is literally the same thing. The reason he used this particular system is for what? It's for steric and bulkiness. What is steric? Steric is what? Non-covalent bonding, right? That's what steric is, non-covalent bonding. So it helps keep this system from breaking apart. Okay? You know, keeping it from breaking apart. That's what bulkiness and that's what steric does. But since I'm working in my computational environment, I don't have to use a big system like this. I can use a small system and show individually exactly how the chemistry works. Okay? So I'm going to use 2-methyl group. I'm going to use 2-methyl group. And from this 2-methyl group, this makes this iron a what? An iron 2. Iron is in group 8, which makes this a D6. So now I have 6 electrons I could play with. Okay? Because I'm using up 2 of my electrons here. Now, for the singlet and the triplet and the quintet system, we see now we have different motifs, different orientation in space of these methyl groups. For this particular system, the bond angle is 120.5. But for this particular system, it's almost linear here, and it's almost linear there, right? It's 148, but this one is 179.5. Linear is 108, so it's almost perfectly linear, which is really good. This system is a singlet. So the bond length are much shorter. One would expect that for the bond length to be much shorter because this is a singlet. It's the diamagnetic system, right? And diamagnetic system always have shorter bond length. This one, the bond length is longer, and this is a little bit longer than that of the triplet. Also, the telltale sign. The original guess when we first started working with this system that the singlet will be lower energetically than the quintet, since this system is holding on much tighter onto the iron. That's not what we saw. What we saw here is that the quintet is lower energetically over that of the singlet by 52.5 kV. And it's lower even yet more of 35.2 kcals per mole. Okay? So what is that telling us? It tells us that we get ready to make this system, what Dr. Power did, starting this system. This system here will start out at a quintet state. Not a singlet, not a triplet. It started at a quintet state. Okay? And in his last paper that he wrote, that's exactly what he discussed. So it started out in a quintet state. So what are we looking for? We investigate the various spin multiplicity of low coordination iron 2 complex via what is free energy surface. Also what? Better understand the key factors that influence the reaction of molecular oxygen with 3D organometallic complex. And also the last one is the current research may help develop a methane to methanol catalysis for the O2 system. Okay? For O2 system, again, oxygen is cheap. We pull it from the environment, right? Okay, so we look at the computed ground state geometries of these di-related species. Now, for sake of time, I'm not going to go through the entire process, but again, it was published. This system here is called a potential energy surface. Okay, it's a potential energy surface. This right here is what we call an MECP, and I'm going to explain what that is. So, stated earlier that the quintet is energetically lower, so this is 0.0, but these things are not really cool. So 0.0, this is 35.2, and this is 52.5 kcals per mole. So here we start off with the quintet energetically relative to the system on this potential energy surface is much lower energetically. Okay? From here, we bound now oxygen onto this metal. Now, once you bound oxygen, they form with this iron 3 superoxide complex. Now, how the heck do you know it's an iron 3 superoxide complex? How do one know that? Okay? You calculate it and you get a picture of that. How do you know that's what it is? Okay? Well, what you got to do to figure out this system is look at system that we already know, right? Oxygen. We know what the double bond for oxygen is like. We know 1.25, right? Look at peroxide. We know what the oxygen bond distance for peroxide is, right? Look at ozone. We know what those are, right? Look at superoxide. We know what those are. So these are systems that we already know what those bond lengths are. So now what we have to do is compare this system, right, with oxygen, which is a triplet. So since oxygen is a triplet, one would assume what? Oxygen is a triplet. One would assume that since this triplet would be lower in energy because oxygen is a triplet, the spin state is a triplet, so therefore you're putting a triplet together, then competitively match, you'd have the lower energy for the system, right? However, we see that's not the case. So what I've done is calculate oxygen. Oxygen is a triplet. Calculate peroxide. We know what the bond distance for peroxide is. Calculate ozone. And then we calculate superoxide. So here are all the bond distance respectively. So the OO in oxygen is like 1.25, 1.23, depends on what you're talking to. Okay, it's a double bond, right? One is a pi bond, one is a sigma bond. You got a double bonded system. So 1.23, and it's highly electronegative. So you're going to pull in those two oxygen together closer than it would for NE, right? 1.35. So here we know that the OO bond distance for this system is a single bond is 1.45, which is almost the distance for that. What? CC bond distance 1.53. Again, it makes sense for it to be lower than 1.53, 1.48, right? Because it's more electronegative system. Here again we have what? Ozone. Ozone is 1.28. Why? Because there is what? There is a resonance taking place in ozone, right? You got a single bond, you got a double bond, you got a single bond, you got a double bond, blah, 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 blah. So it's not going to be 1.23, it's going to be a little bigger, longer than 1.23, 1.28. And then now for superoxide, we got a 1.37. Whoa, look at this. 1.37. The bond distance for this species right here, this system is 1.36. So what would you call this oxygen up here? The bond distance is 1.36. The superoxide bond distance is 1.37. What would you call that? It's a superoxide complex. It's a superoxide complex. You have to get that system. It's a superoxide complex. So which is good because what that is saying that I have what? An electron ready to do some work. I have like a radical electron ready to do some work. And we know that radical don't want to stay radical too long. They want to find something to attach themselves to, right? Right? So this is beautiful. And what we have seen here is that this system goes through a transition state to form a diaxal complex. It's split up to form a diaxal complex. However, you know, I'll spend a little bit more time on this than I want. However, you see now we start from the singlet here. Transition state here is the quintet. This is a triplet. However, once you go through the transition state, guys, it falls back onto what we call a singlet circuit. It falls back to a singlet. It falls back to the singlet. Now the singlet is lower in energies. From here, it falls back to the singlet. So the system starts here in the quintet state. It goes up. It goes up on the transition state. From here, it spins flip and come back down as a singlet. Okay, but it starts at a quintet, but it's spin flip to what? A singlet. And the question one could ask, why did it do that? Why did it do that? Why did it spin flip from that of this motif to this motif? Because this motif looked more like a square planar complex. Okay, looked like more like a square planar complex, not a tetrahedral, more like a square planar complex. And most square planar complex are singlet. Okay, it's because of what? Because of the orbital splitting, right? Because of the orbital splitting. Okay, this is what? X, Y, X. So this is what? X squared minus Y squared. This is X, Y. This is a Z squared. This is X, Z. This is Y, Z. 1, 2, 3, 4, 5, 6. Right? So here we have the splitting taking place right here. The electron cannot jump all the way up here. Up here, it's so high. The x squared minus z squared for this system is so high all the way up here. The electron can't jump up there. So what are you going to do? According to what? Not even Hunch rule, right? According to Pauli exclusive principle, you're going to form in this particular motion. So 2, 4, 6 electron form in this particular motion. right here. Because it looked, you can turn that off, it looked more like a square planar complex, not a tetrahedral complex. And then from here, the other thing take place from the singlet. Before the transition state, he did another spin flip and went back to where we started, which is a twist, right? So we call